Hi, my name is Madison Smith, and this is my Lab 4 on circuits and capacitors. So the purpose of this lab is to predict and test our predictions with measurements of current and resistance throughout a circuit, also to demonstrate how the charge on a capacitor is a function of time, as well as the voltage in a light bulb due to the charge on the capacitor when they're connected, when they're not, and how the capacitor charge influences the light bulb, and then the conservation of energy in a circuit. So some key principles I wanted to point out was the conservation of charge. So the total potential difference over the entire current should sum to 0. So no energy is going to be created or destroyed, just moved around the entire circuit. The node rule is that the sum of the currents flowing into the node is equal to the sum flowing out. And then the loop rule is that the sum of the changes in potential difference around any potential around any closed loop must equal 0. So my prediction for the current for I1 and I2 was using the loop rule and the node rule, and I calculated it would be 0.02 amps, which is exactly what the ammeter reads, so I was correct in that prediction. Also, when the circuit is reversed, or when the ammeter is reversed, it is still going to read 0.02 amps. And when it is disconnected and only connected by the voltmeter, it's going to read 3 volts, but the ammeter will show 0 because the circuit isn't actually connected and no current is flowing. So to show the potential differences around different points around the circuit, so the only ones that are going to be different are going to be points A to B, which is across the battery, and then C to D and E to F, which are across the resistors, and that the sum of those should equal 0. So that's why 3 volts minus 0.96 minus 2.04 is going to equal 0, which is what we want. For part 8, we were graphing the potential versus the position around it, so that's what it shows there, and I just added on to the graph that we were given. And then when you attach a voltmeter, it's not going to change the amount of current because it's not adding anything, so you can't create anything, so it's just going to continue moving around. And then we calculated the resistance over the 2 resistors, the wire, and the ammeter, and those are going to be shown there. There's only going to be resistance on the 2 resistors because for the wire, the potential difference is only going to equal 0, so the resistance will be 0 ohms for those 2. So for part 3, we're testing the effects of a capacitor, whether it's charging or discharging on a light bulb. So on both of them, whether or not the capacitor is charging or discharging, it's going to start out really, really bright, and then as it's charging or discharging, the light is going to dim over time. So we're going to use that observation that we did with the lab and the calculations in the next portion. So what I did was over a span of 20 seconds, I calculated the voltage in this circuit that's set up in the top right corner, and then I took the natural log of that voltage over the initial voltage, and that's what's going to be graphed in the bottom. And so I did that through the calculations that the potential difference of the capacitor plus the resistor are going to both equal 0. So we did some algebraic manipulation, and that the natural log of the voltage over the initial voltage is going to equal negative T over RC. And so we use that to calculate that the slope is going to equal negative 1 over RC. So we calculated RC was equal to negative 6.48, which is equal to what I found in the simulator. In conclusion, so what if we were doing this in real life and used an actual ammeter instead of the simulator? So a real ammeter would not be as accurate. It would cause some resistance. So it would affect the current flowing through and the voltage. So what if you're doing this in real life and use a real battery? So because if you were using a real battery and real wires, they wouldn't be acting as perfect as this simulator. So it would take more time to charge the capacitor because there was going to be that resistance with everything not being as perfect as a simulator. So thank you so much for listening, and let me know if you have any questions.